In the second part of my talk, I'm now going to talk about hardware errors and how they affect the operating system and the software layers. Um, let's look at what hardware errors means in theory at this point. In general, any kind of memory or logic circuits you have in your hardware are built from transistors, and this is a very simplistic model of such a transistor. Usually you have some parts called source and drain, and if your transistor is supposed to have the state 1, then current is going to flow from source to drain, and if it says the state 0, then there should be no current. And semiconductor technology works by putting some isolator in between, which is called the bulk. And on top of this transistor, we have a gate diode, which is supposed to switch the transistor on and off. And the gate diode is separated from the rest of the transistor with through some kind of oxide layer. Okay, so now there are a couple of things that can go wrong in such a transistor. And one source of errors that happen in transistors are radiation-induced errors, which may come from cosmic radiation, but they can also come from natural radiation, which stems, for instance, from the packaging of your processor, which is the part that contains the processor. And for instance, back in the 1980s, Intel had a problem where one of their chip factories was located some miles down the river from a uranium mine. And it turned out that all the packaging that was built in this factory led to the processors suffer from alpha particles that originated from this packaging. And it's just something that you need to control. In this case, Intel just closed the factory and built it somewhere else again. And cosmic radiation, however, is not something you can control as much. So there is some kind of distribution, and if you're at the sea level, you're going to see fewer radiation than if, for instance, you are in an airplane or in a satellite. However, this is already also becoming a problem at the ground level. So what happens with radiation? So in the end, what a transistor does is you have this gate and you apply a current between the bulk and the gate, and this creates some kind of a condensator which allows current to flow. And in order to perform this switching and create this electric field, you need to apply a certain threshold voltage, which is the switching voltage for the transistor. And if you have cosmic radiation, then this radiation may pass through the transistor so that it looks like the transistor switched from 0 to 1 or from 1 to 0, depending on what kind of transistor you have. And as transistors grow smaller and smaller, we have fewer atoms and fewer electrons in a single transistor. And this in turn means that the actual charge that you need to switch the transistor between its states also becomes smaller, as also with the threshold voltage to switch the transistor becomes smaller. And this in turn means that lower powered cosmic radiation is now also able to already switch a single transistor. Another source of errors comes from aging and thermal stress. Thermal stress means when you switch your transistor on and off and on and off all the time, then of course you're inducing a certain temperature and things may go wrong from that. And the other sources in terms of aging happen that, for instance, the connectors between your transistors are made of metal. And if electrons pass through this metal when a current flows, then they may push certain atoms in the connector out of their position, and this creates holes in the connector. And if there are holes, then no current can flow anymore because there are no electrons available anymore to carry the current. So you basically end up with a wire that is not able to transmit current anymore. And this effect is called electromigration. Another effect that may happen is when you have your transistor, then what you usually want is that current flows from source to drain. However, the conducting particles usually do not only pass on a straight way between source and drain, but some of them will end up being pushed into the oxide layer that separates the oxide from the gate. And this leads to two other effects called hot carrier injection and negative bias temperature instability, which in the end lead to the oxide layer wearing out or becoming charged with either positive or negative particles. And when this happens, then the threshold voltage of your transistor also changes, and it might either change to a very high value, which means you cannot switch the transistor anymore, or it may change to a very low value, which means the transistor is also not going to switch anymore because it's simply always having the state 1. And these effects, as I already told you, are amplified now that we are seeing smaller and smaller transistors. And this in turn leads to some studies that were conducted or which try to figure out how often this happens in the real world and how these errors actually manifest at the software level. And there's a study from 2005 where a guy called Sajizi tried to evaluate how hardware errors affect software by injecting them into an FPGA model of actual hardware. And one thing he found out is that 85% of the hardware errors he injected were actually masked by the hardware. And masking means that the error will never appear in software. So even though you have some kind of a transistor that fails, this transistor is not having effect on the software that's running on top of your system. And this happens, for instance, in terms of logic gates, like your arithmetic logic unit or some multiplier units, which may only be affected by an error if the error hits at exactly the right point where the arithmetic unit, for instance, is also going to make a certain calculation, or where it's waiting for a rising flank of the current CPU cycle to perform the next computation. And if the error hits in between and the ALU is currently not willing, for instance, to read inputs, then an error affecting the inputs will also not lead to an error. Another thing they figured out is that the outcome of errors, if they hit software, also depends on what kind of hardware unit you actually affect. So for instance, they had a look at memory errors, and in memory errors, it is more likely to happen that you silently change some data in your application and the application still continues running but produces a wrong result. Whereas, for instance, if you have a look at the execution unit, like the instruction decoder, then decoding the wrong instruction may actually lead to an application crash, more likely. Another study was carried out in 2008 where people focused on permanent errors. So the previous errors, like or radiation-induced errors, are usually transient. And transient error means the error occurs at a certain point and also vanishes after some time. Suppose, for instance, if you have a memory error, then the error occurs because of some radiation, and some bit in memory changes from 0 to 1. But if you do not read this bit and overwrite it later on, then nothing is going to change and the error is not going to affect you. In contrast, in terms of permanent errors, which for instance are the aging effects I was talking about previously, you may actually not fix this problem easily by simply overwriting the state. And this is also something the study pointed out, that permanent errors are less likely to lead to situations where simply some data is going to be changed, and they are more likely to lead to real crashes and hardware exceptions, which is in turn not that a bad thing. Of course, still your hardware is broken, and you're going to have to do something about fixing this problem. However, actually seeing a crash or a hardware exception is good, because at this point you know something went wrong in your system. And knowing something went wrong is the first step to fixing the problem. If in contrast you have some error that simply modifies data and the data still looks valid to the program and the program still keeps processing it, then you have no chance of figuring this out. Another thing that this study then pointed out is that even though if you have a permanent error, you're very likely to see a crash, which you can take care of. 65% of the errors that they injected were actually corrupting the operating system state, which is something we need to care about. Other studies had a more closer look on how such errors affect microkernel operating systems. In this case, they had a look at operating systems called Koros and LynxOS. And the important point they found out was that you have a significant amount of errors that do not change the the performance or the behavior of your application. And these are actually errors that contain an optimization potential. Because if you come up with a certain mechanism to detect and correct errors, then you're going to induce some kind of overhead in terms of either you need to do additional checks at runtime, so your program is running slower, or you're adding certain hardware that performs this checking, then you're adding energy consumption and you're adding space on the chip that you require for that. And if there are errors that you do not need to detect because they're not going to change anything in your program, then you have some potential for optimizing here, because if we can avoid detecting and correcting those errors, we can save the overhead that is involved with fault tolerance. And the last study I'd like to point out is some weird study that had a look at C programs and figured out that if you have dynamic branches in a program, which are branches based on certain conditions. For instance, if you have a loop condition and want to branch to the start of the loop if your for loop counter is below a certain value, then if you have such dynamic branches, then in up to 40% of the cases for a certain benchmark suite, they figured out even if you take a different branch because your condition is now broken and you're jumping into the other part of your if-else branch, the program state is still not affected by this. It may diverge for some time, but after a really short period, programs tend to get back to the same code path with the same data than before. And they analyze a couple of programming constructs that make it easier. And the main point to take away from these studies is that hardware errors are a problem. They will appear in software in some form. This form may either be that your system simply crashes or that you see hardware interrupts or exceptions that you would not have seen otherwise. However, there are also situations which where an error does not affect your system at all. And this in turn leads us to some challenges and opportunities we have when we talk about taking care of errors in software and hardware. And the one thing is we have a challenge in that we need to detect and correct hardware errors in software. This is something that sounds weird at the first place, because the hardware, of course, is the thing that your software is running on top of. And how would you write software that is able to figure out that hardware is not functioning correctly? Because the software usually trusts the hardware to function correctly. However, there are, as we will see, there are ways to do so. And the challenge is to do it properly. Then I already pointed out that we have this potential for optimizing performance by only tracking those errors that will actually do harm to our system. And if we have errors that don't harm the system, then we simply do not want to track them at all. The next challenge is if you have a look at today's systems, then you have a lot of applications where you only have the binary code for or the binary form of the application. Of course, if you simply only think of open source software, then you can download the source code all the time. However, if you have a look at the practically used software today, then a lot of applications are either completely distributed in the binary form, or you have certain parts of an application, such as libraries or certain drivers. Think of graphics drivers, for instance, which are only available in binary code. And this in turn means that we have some solutions which you cannot apply all the time. So for instance, there are compiler-based solutions where you use a special compiler, and the compiler generates machine code that is performs additional checks so that you can avoid hardware errors. However, in order to apply such compilers, you need to have the source code of the application, and you may not always have that. And the last optimization potential is that if you have a look at modern hardware, then we have a lot of hardware level concurrency. So these days, even in your laptop, you get 4 or 8 cores that you can use for processing. And these processors are most of the time idling around anyway, because your system or the software you're running is not making use of them at all. So there's some optimization potential here, because we can use this hardware level concurrency to perform additional checks or to track hardware errors. Okay, if we have a look at systems or solutions that take care of fault tolerance, we can try to map them into some coordinate system. And the y-axis here distinguishes between systems that take care of software errors and those of taking care of hardware errors. So we already talked about soft errors in the first session, and we're now more interested in hardware errors. And on the other hand, there are solutions that work on commercial off-the-shelf systems, which is simply computers that are created from components that you buy from the shop next door. So your usual laptop or your usual PC at home is going to be commercial off the shelf. hardware, whereas other systems are non-commercial off-the-shelf hardware where you have special hardware that's built for a certain scenario. And this is usually used, for instance, in avionics or in space, where you have certain requirements and where you build your processor to deal with those specific requirements. If we have a look at this, and we have a couple of solutions that are solely at the hardware level in order to take care of hardware errors. One thing which, for instance, you find in satellites and spacecrafts are radiation-hardened processors. And a radiation-hardened processor is a processor that has been explicitly built to be used in an environment where you have a lot of radiation, such as cosmic radiation, and that has dedicated hardware units that allow you to tolerate errors. For instance, by placing 3 CPUs on the same board and performing the same actions and comparing the states of the CPUs all the time. And this is, of course, very expensive. And if I'm saying very expensive, then, for instance, if you have a look at the CPUs that are used in the Mars Curiosity rover, that's the last vehicle that NASA put onto Mars, then a processor is rumored to cost about $200,000 a piece, which is fairly expensive. Another technique at the hardware level is called redundant multi-threading, where you exploit the inherent parallelism in modern CPUs, which is, for instance, available in x86 through hyperthreading, to not perform more work, but instead perform the same work twice, and again compare what the multiple hardware threads output into memory by writing into memory or by issuing calls to certain devices. And thereby, if you have 2 threads and they perform the same work, then you'd expect them to also generate the same outputs in the same order. And if something is mismatching in there, you can detect errors this way. This has been also done in hardware and is still fairly expensive. The next systems we have are traditional mainframe systems, which you can buy from IBM and HP, which are called like z/OS or HP Nonstop. These systems are there to tolerate some hardware errors, but they're mostly focusing on tolerating software errors. Systems are getting cheaper now. We're not paying several $100,000 per CPU anymore, but you're paying $100,000 for a whole system, which can be better or not. However, what these systems usually do, apart from being still very expensive for use at your home, is they force programmers to use, for instance, specific programming models. So, for instance, HP Nonstop uses a programming model called process pairs, and they're only providing you with certain fault tolerance guarantees if you adhere to this programming model. So you're not completely free in what you want to do in your system. And then we're coming to the commercial off-the-shelf world, where at the operating system level, we have Minix 3, which we already talked about. We have another L4 variant called SEL4, which is dedicated to dealing with software errors. And in the case of SEL4, they're actually performing formal verification of the whole operating system kernel. And by performing formal verification, they're not dealing with software errors, but they're mathematically verifying that there are no software errors in the code. And by doing so, you can, of course, make sure that your application is protected against software errors because you know there are no software errors. However, these systems still make the assumption that the hardware underneath is working correctly, which, as we saw, is not the case all the time. So finally, in the commercial off-the-shelf world, we also have compiler-level solutions such as Swift and encoded processing, which, as I explained before already, generate specific machine code. And this specific machine code is then intended to perform additional checks. For instance, one thing you can do is, if you have an instruction and you believe this instruction might be affected by a hardware error, you can perform this instruction twice using different resources. For instance, if you have add register AX and BX, you can perform the instruction again by adding a register CX and DX and putting the same values into A and CX and B and DX. And thereafter, after performing these instructions twice, you can compare the results in the different registers and they need to match. And Swift and encoded processing are actually generating machine code that does exactly this. Of course, this incurs a certain runtime overhead because you're doing work twice or 3 times. However, it allows you to find certain errors that affect your registers, that affect certain state in memory, and so on. Unfortunately, these solutions, as I explained before, only work for software where you have the source code, because otherwise you cannot recompile them. And we try to address this issue and come up with an operating system service that is able to deal with the same errors that Swift and encoded processing address. However, that does so at the operating system level and thereby also supports binary-only applications as workloads on the system. And this software service is called Roman, and this is something I'd like to talk about in the remainder of this session. One fundamental assumption Roman and any kind of other fault tolerance mechanisms make is that applications are deterministic. And by deterministic, we mean that an application performs certain computations, and this computation is controlled by the inputs that go into the application, and the application, after computing, generates a couple of outputs. And if an application is deterministic, this means that if you pass the same inputs to the application, you're also going to see the same outputs. And this assumption usually holds in traditional single-threaded applications. And if we have a deterministic application, what we can then do is we can take several instances of the same application. So this is 3 times performing the same amount of code or running the same code. We can collect the inputs going into the applications and pass them to all the 3 instances of the application. And then we can monitor the output of the application. And because the applications are deterministic, if no error happens, they will generate the same output for the same inputs. And therefore, we can compare the outputs in the end and then either continue execution if everything was fine, or if we detect that something went wrong, we can start correcting this error in some way. So in the terms of Roman, so in general, this whole process is called replicated execution. And this is what Roman does on the L4 Fiasco microkernel. In our case, inputs come from things such as system calls, shared memory, I/O memory. There are some special instructions that also may modify program flow. For instance, instructions reading the CPU timestamp counter, because the application may decide to perform different actions depending on the timestamp. And there are, of course, also hardware interrupts, which may be inputs to your application that trigger certain actions. In terms of outputs, again, we have system calls. So depending on some inputs, the application may perform other system calls. It may perform writes to shared memory, access some I/O, or even trigger hardware exceptions, such as page faults. And this is the whole thing Roman does. It monitors the inputs going into an application, monitors the outputs, and compares these things between different instances of the same application. And by replicating an application, Roman is then able to detect errors if the application performs different system calls, for instance. This whole concept is not completely new and has already, for instance, been implemented for Linux using a binary recompiler. Binary recompiler is special in contrast to the compiler level works I talked about before, in that these tools are really able to take a binary and generate a new binary from it. So actually, you could use a binary recompiler to generate new fault-tolerant code from existing binary level code without having the source code of an application, which is kind of cool. However, there are some disadvantages in that. For instance, you have to write this binary recompiler, which can be pretty hard to do for x86. Apart from that, this work done on Linux called process level redundancy previously did a similar thing which the Roman framework for L4 does, and which I'm going to talk about on the next slides for Linux. They also used system calls for monitoring inputs and outputs, and they used virtual memory for fault isolation. This is some design principle that we already saw in Minix. In Linux 3, you also have fault isolation by putting applications into different address spaces. And in the case of process level redundancy, we're putting the same application into different address spaces by running it 2 or 3 times. And thereby, we can be sure that if an error occurs in one of the applications or one of the replicas, then it will only affect this single replica and the other replicas continue running unaffected. However, in the case for process level redundancy, this is also a restriction because they only support protection of user level programs on Linux. In contrast to that, in Roman, we try to avoid using a binary recompiler because this is a really complex piece of code. we add additional synchronization events by not only monitoring system calls, but also access to shared memory, page faults, and so on. And by exploiting a microkernel architecture, we're not restricting ourselves to replicating user-level programs, but we can also apply replication to traditional operating system services such as file systems and device drivers. This all ends up in a replication-aware operating system architecture. And this architecture is based on the traditional way of how we do software development on L4. So on top of that, we have applications running on top of L4. We have our microkernel running, and we have a runtime environment, which is the L4 runtime environment in our case. And what we now add is we add a replication service, which is called Roman. And Roman then runs multiple instances of this application, so we get a replicated application. In addition to that, the whole operating system architecture is also able to support unreplicated applications. Why is this an advantage? So in traditional hardware level solutions, for instance, you can statically replicate applications by, for instance, by having redundant multi-threading in hardware. And your hardware level hyperthreads are then used to perform replication. And whatever application you run on top of it, it will always be replicated. This is a problem in systems where you have multiple applications, which may have different views of how vulnerable they are or how much protection they want against hardware errors. You may have applications that really require protection because the programmer did not do anything to protect them from errors at all. And you may have other applications that are already protected or where you don't need any protection because the application is going to restart itself every few milliseconds anyway. And in this case, building replication as an operating system service gives you the flexibility that the operating system can decide which application needs to be replicated and which does not. Whereas in a pure hardware solution, you simply would replicate everything and thereby overcommit resources and consume, for instance, more energy than you need. And as I already said, by basing our work on a microkernel, we not only replicate traditional user-level applications, but we can also apply the same concept to operating system services. So this leaves us with one problem. We're now building this whole operating system architecture that allows us to run applications in a replicated manner and thereby detect and correct errors, which is a good thing. However, we have still a few components below the replicated applications, which are required so that the system works. And these components are the microkernel itself, some parts of the runtime environment, and the replication service Roman. And these components cannot be protected by actually replicating themselves because this is kind of a chicken and egg problem. You cannot use the replication service to replicate the replication service. This doesn't work. So we need to find some other measures to protect this layer down beneath here. And let's first give this layer a name. We call this the reliable computing base, because this is similar to the trusted computing base in security. The reliable computing base is all the code that you need to trust in order to gain replication and gain fault tolerance against hardware errors. And in the end of this talk, I'm also going to describe some ideas on how we can protect this part of the system. But first, let's have a look at how Roman actually works. When starting an application using Roman, we split the application into different address spaces. The first address space is the master address space, which is in control of the whole replicated application. And there's one master address space for every replicated application. And one thing the master does is it creates multiple instances of the same application, and we call these instances the replicas. And the master then uses fiasco mechanisms to monitor whenever the replicas perform any actions that are visible to the external world. And in terms of fiasco, these actions are usually system calls that perform sending IPC messages that interact with kernel objects and so on. And whenever something like that happens, we use a fiasco feature called virtual CPUs to not let the replica directly perform a system call, but instead to intercept the system call in the master so that we can then compare whether all replicas perform the same system call. Apart from that, whenever the replicas do not perform system calls but just perform internal computations, the master is not involved at all. The replicas then run completely independently, and they can even be scheduled on different physical CPUs, which gives you two benefits. One benefit is that if you run them in parallel on different CPUs, you lower the runtime overhead you get from replicated execution. Because if you ran them on the same CPU, you of course would spend 3 times the time, the amount of computation than running the application only once. However, if you distribute this across multiple CPUs, because we have so many CPUs in modern systems, we can decrease this overhead. The other thing you gain from running on multiple different CPUs is that, of course, if one of your CPUs has a fault, the other CPUs will not be affected, and so replicas running on the other CPUs will not encounter this error. And therefore, you also increase fault tolerance by running on some kind of a multi-core CPU. Okay, so the master now intercepts all system calls and anything else where the replica interacts with the outside world. The master also gets to see page faults. The master gets to see any kind of hardware interrupts that happen when executing the replicas. And anytime this happens, the master performs state comparison. And as our replicas are deterministic, we know that they always would generate the same system calls with the same parameters. And if this is not the case, we detected an error and can correct it. The next thing the master also does is it needs to deal with the system calls the replicas do at some point. For the outside world, so applications running outside this replicated application, we still want that it looks like this is only one application, because otherwise you have to restructure your whole system. However, we only want to get fault tolerance for the application, but in the end, for an outside user, it should still look like this is a single application interacting independent of how many replicas we have and so on. So what happens when our 3 replicas perform a system call is the master actually performs the system call once on behalf of the replicas. The system call is not executed 3 times. And the master then waits for the result of the system call and injects this result into the replicas and then lets them execute again with this identical results. So this is one of the tasks the master has. The second task is resource management, because in some ways the master needs to be in full control over how resources are assigned to our different replicas. And we're going to see now where this is a problem. The first resource the master needs to manage is capabilities. I suppose Udo Steinberg already told you about the Nova system this morning and told you about how capabilities and portals in Nova are handled. And in Fiasco, we have a pretty similar mechanism. And in Fiasco, this mechanism is that every application has a task local capability space, which is simply a table containing pointers to certain kernel objects. And kernel objects can be anything from communication channels to address spaces to threads in the system, any kind of abstraction the kernel provides you with. And this capability table is maintained by the kernel, and you as an application do not have control over this table. The only thing you can do is you can allocate slots in the table, and you can perform system calls. And when doing a system call, you can indicate that you want to perform a system call using a certain slot of this table, and thereby you indicate that your system call should affect a certain kernel object. So for instance, if this table entry points to a communication channel, then the action you perform would actually be sending a message through this channel to the other side. And if this slot, for instance, points to a thread object, you would then simply perform some thread management operations, such as setting the thread's priority or modifying the thread's instruction pointer or something like that. And what now happens if we have an application, we have our capability table, and at runtime, the application will start allocating slots in this capability table. And these slots will then have some local meaning to the application and will be used at runtime. If we have a replicated application, because the applications are deterministic, the second replica of our application will have the same state for this capability table. So in our case now, both replicas will have the same layout and will have slots 1 and 2 in their capability table used, whereas 3, 4, 5, and 6 are still free. Now in the Roman system, we also have the master. And the master is an application on its own, and it will perform actions on behalf of the replicas. It performs management duties. And so what's going to happen when the master executes is the master will allocate some capabilities of its own, like in this example here, capabilities 1, 2, and 4. And it will map other capabilities into its capability table, which match to the or map to the capabilities used by the replicas. And this is now a problem because in Fiasco, when you perform a system call, you specify the capability you want to perform this system call with. And the way you specify is simply by saying, okay, this is an integer value here, and this integer value refers to a certain capability slot. And the problem is that depending on what kind of message you're sending or what kind of system call you're doing, you may have integer values and capability indices and other data intermixed. And the master, of course, is able to intercept system calls, the replicas do, but the master is not able to decide whether a certain integer value in the system call parameters is either a capability index, which needs then to be translated. So for instance, if replica 1 does a system call and uses capability slot 1, the master would have to translate this into a system call that actually uses his local capability slot 3. However, the problem is capability indexes are simply integer values, and the master is not able to distinguish real integer values from capability slots, unless, of course, you write the master in a way that it is aware of any kind of system call your application can perform. But in this case, you have to rewrite your master for every application, and this is a hard thing to do. So we need some other way of doing or of managing capabilities in our system. And the way we do it is we partition the capability space. The master is, of course, responsible for setting up the replicas once they start. And at this point, the master can set up the replicas in a way so that a certain part of the capability table is marked as this is already used. And then the master is in control of his own capability table, or at least the indexes in there, and can make sure that the part that is marked used for the replicas is used to store master private capabilities locally. And the other part that is marked as available for the replicas is used in the master to only store replica capabilities, but not master private capabilities. And as we are in control of replicas during startup, we can set up the system so that this is always happening, and this is always the case. And if we do this, what we get is we get a one-to-one mapping between replica level capability indexes and master level capability indexes. So when replica 1 now performs a system call on replica 4, this will be replica number 4 in the master as well. And by doing so, what we now gain is the master can simply take the system call as it would have been done by the replica and perform it on behalf of the replica. And we can be sure that whenever a capability index is inside this message or inside the system call parameters, it will be used properly because capability meanings have the same or capabilities have the same meaning for the replicas and the master. The next resource we're going to have a look at is replica memory management, and this is the second big thing you need to take care of when working with applications on L4. And consider your replicas now. Here we have address spaces, and we have certain segments in these address spaces which contain data. And of course, again, our replicas are executing deterministically. So the layout and so the size and the ordering and the layout of these memory segments is going to be the same in the replicas. In addition to that, we have the master address space, which may contain different regions of memory. And what we now do is, if we have read-only memory, we can have a single copy of this memory region in the master, and we map this region to both replicas from the same source. This works because as long as the replicas only read memory, they don't need their private copies because read-only memory is not going to change anytime soon, and they can still independently read data from there and access them. If, however, we have writable memory, the master needs to create a dedicated copy of this region for every replica. The reason here is that replicas should execute independently as long as they can, and during independent execution, the replicas might, of course, read and write data from and to these writable regions. And depending on how far replica 1 would be ahead of replica 2, if we modify or if we took the same source in the master and mapped it to both replicas, replica 2 might see the wrong values or different values from replica 1 and might then lead to different behavior, which looks like an error, and we need to avoid that. And in order to do that, the replicas get their own private copies. One thing to note is that this whole concept of having private and copies and having shared read-only copies of memory only works as long as our memory works correctly. And as we're dealing with hardware errors, of course, we could also say, well, memory is also hardware and memory could be broken as well. And in this scenario, where we have shared read-only regions, we assume that memory is somehow protected by hardware-level protection mechanisms. For instance, if you have a look at modern server installations, then memory is usually protected by error-correcting codes in hardware anyway. And if you have such ECC memory, you can be sure that memory content is not going to be corrupted by any kind of hardware errors. And if you have this, then you can make this optimization that read-only regions are shared across replicas. If you need to assume that your memory is broken because, for instance, it is not protected by error-correcting codes, or because you do not believe that your ECC protection is enough to detect all errors, then the solution would be to take the read-only regions and again have dedicated copies of these regions for every replica. Because then, again, one error in one of those regions will only affect one of the replicas, and the others will continue executing with the correct values and allow you to detect the error later on. Okay, so what we talked about so far is Roman replicates applications at the level of operating or of user level applications, and it intercepts system calls in order to figure out what inputs go into the applications and what outputs come out of them. There are a couple of other ways how inputs and outputs can reach the application, and one of those are shared memory channels. A shared memory channel is when you have two applications that establish a certain piece of memory that is mapped into both address spaces, so that reads and writes to those regions become immediately visible to the other end of this channel. As the Roman master process is only in control of a single application, it loses control of shared memory regions, because there may be an external application which may be in control of another master process, or which may be running without replication at all. In this case, no one is in control of this application. And so shared memory channels cannot be they cannot be protected using the master and the replication approach. And they can also not be assumed to always be correct, because we simply do not know what is going into the applications through those shared memory channels. And one solution to this problem is a technique which is standard in today's virtual machines, and this is called trap and emulate. And what this does is it takes the shared memory region and makes this region inaccessible by marking it inaccessible in the application's page table. And then whenever one of the application tries to access this shared memory region, you will get a page fault. And then in a page fault handler, this page fault will then be delivered to the master process, and the master can then have a look at the current application state. It can figure out what kind of instruction is now being executed, and then it could emulate this instruction by manually in the master performing this memory operation. This has a problem, and for one, this is fairly slow, because for every instruction that accesses memory in terms of a shared memory channel, you get an overhead of a factor of 100 or up to 1000, because you're now not only executing one memory instruction, but several instructions. The other thing is it also adds complexity. So we wrote a small disassembler for x86 that allows us to figure out what instructions are executed by an application accessing shared memory. And this already sums up to 6,000 lines of code simply for an x86 instruction disassembler. And then we wrote an emulator that is able to execute or to emulate the most or the easiest instructions, such as read and write to a memory address and push and pop from and to stack and so on. And this was another 500 lines of code. And so we're getting 6,000, 7,000 lines of code simply for this trap and emulate thing, and it's even slow. So we thought about another technique and thought about whether we can avoid having traps and emulate. And in our case, we have a different a different way of supporting shared memory channels for replication, which we call copy and execute. And copy and execute works like this. We have our master address space and our replica address space. And in the case of a shared memory channel, we make sure that in the master and the replica, the shared memory channel is mapped to the same virtual address. So this means whenever the replica accesses the memory virtual address in its address space and the master intercepts this, the master knows that this access will go to the same virtual address in his address space. Now, if the replica executes code and starts, for instance, moving something from register EAX into the memory location pointed to by EBX, we will get a page fault because we make sure that the replica has no real access to this memory region. So there will be an access to this location somewhere in the shared memory channel, and this access will be translated into a page fault by the underlying hardware because the access rights are not set. And the master will receive this page fault by means of the Fiasco page fault handling mechanism. So in Fiasco, anytime a hardware page fault arises, this hardware page fault is translated into a IPC message that is sent to the master that is in charge of this application, or to the page fault handler in general. So the master thereby figures out, okay, the replica is accessing the shared memory channel, and instead of now performing trap and emulate, so this is the trap part of trap and emulate, and instead of now interpreting the instruction and emulating it, the master performs a small trick. And this trick consists of having a buffer here, which has three parts. The first part contains a couple of assembly instructions that load the replica's thread state into the current CPU. Then we have a couple of no-op operations in here. And the final part is then code that restores the current CPU state into the replica CPU state. Note that whenever the master receives a trap notification from a replica, sorry, the master will always also obtain data or obtain a view on the replica's architectural register. So this is how the replica state can be loaded into the physical CPU in this part. What happens in the next step is the master figures out which instruction the replica was going to execute, and then copies this instruction into the no-op buffer over here. And what we get from this is we get a buffer containing instructions that take the replica's state, load it into the physical registers, then perform the faulting instruction in the master address space instead of the replica address space, and thereafter restore the physical CPU state into the replica and the previous master state into the physical CPU. So this is in some way, this is also what the emulate part of trap and emulate does. However, instead of having a look at the instruction and having to figure out what the operands are and where the source and the target of a memory operation are and what needs to be done in addition, we simply execute this on the physical CPU, and thereby basically we're using the fastest instruction emulator we have available, which is the physical CPU. And so the outcome of this is copy and execute avoids a lot of the complexity that you get from emulating instructions, especially in x86, by simply not inspecting instructions at all. It's also slightly faster than trap and emulate because we're simply executing an instruction is much faster than emulating it. However, it's still way slower than traditional memory access. So copy and execute may be a nice idea, and it also reduces the complexity of the code that you need to implement it, but it's still slow, and the outcome of this is then shared memory handling in general is unfortunately fairly slow. So now that we executed this buffer, in the end, later on we switch back to the replica, and then the replica continues executing whatever it did before. All right. So with all these things in place, we now measured the runtime overhead that we get from replicating applications using Roman, and we used the spec in CPU integer 2006 benchmark suite for that. And one thing we see here is so baseline performance is 1. So these are the normalized overhead values. And we did 3 experiments. Actually, we did 4 experiments. One was to execute each benchmark natively on Fiasco without any interaction in Roman. And then we have the yellow bars, which indicate single execution. This means we have a single replica running with Roman on top of L4RE. And this any overhead that's coming from single execution is actually the overhead that we get from intercepting system calls in Roman and proxying them to the kernel instead of directly letting the application call the kernel. The second bar, which is the orange ones, indicates the runtime that we take for double modular redundancy, which means we're having 2 replicas running on top of Roman, and we compare the replica states whenever they perform system calls. And the last bar, the dark red one, is triple modular redundancy. And in triple modular redundancy mode, we're actually executing 3 replicas. Why are we doing this at all? So in double modular redundancy, we have 2 replicas, and if one of the replicas is broken, what we're going to see is we're going to see a difference in the states between the first and the second replica, but we will not be able to tell which of the replicas has the error. So the only thing we can do is we can stop the application and restart it, similar to what we would do in a case of a software error. However, we cannot correct this error, and restarting an application may take some time. In triple modular redundancy, when we have one application that is affected by an error, we still have 2 other applications that are correct. And this means we can have a look at the replica states and figure out which is the broken replica. And then we can directly correct this error by overwriting it with a state from a correct replica. So what you get from running in triple modular redundancy is you need to pay more runtime overhead, but you get the opportunity to fairly fast correct the error and continue running without having to re-roll the application or restart the application. Okay, what do we see here? So the first thing is the yellow bars. Sorry, the yellow bars are already all very close to the 1 mark. So there is reasonably pretty much no overhead from simply running an application in Roman compared to traditional L4RE mechanisms. And in the other cases, in most benchmarks, even for triple modular redundancy, overhead is below 5%, which is fairly good in our example. There are a couple of exceptions, however. One of the exceptions is this GCC benchmark here. And in this case, the GCC benchmark unfortunately does a lot of system calls related to memory management, and the overheads here actually result from the fact that memory management in Roman is not implementing everything that the GCC benchmarks need, and there's some room for optimization still left. And then, however, there are 3 other benchmarks which have fairly high overheads, which is the 429, 462, and 471. And for those benchmarks, we more closely investigated what's going on, and we figured out, well, this is not a problem related to memory management, but this actually stems from how we place replicas on different cores. The background here is that the system we tested this on was a dual socket machine, and we had 2 sockets in this case, where each socket contained 6 processor cores, and these cores each had their own local L1 and L2 caches, and 6 cores each shared the L3 cache of the current socket. And what happened here is, for these 3 applications with the high overheads, the L3 cache actually became the bottleneck because the applications were cache bound, they were processing a large amount of data, and they required even a single instance of these applications already required a large amount of the cache for itself. And now if we're running 3 instances, each using their own copies in memory, we run into the problem that the cache does not suffice to keep all the data that is required. And so we have to go back to memory, and this is where this overhead comes from. We fixed this problem by assigning one of the 3 replicas or one of the 2 replicas to the second socket on our machine. So in the end, our machine had 12 physical cores, and 6 of them shared a socket. And what we now did is we distributed the replicas. Replica 1 goes to the first socket, replica 2 goes to the second socket, and if we have a third replica, we put it on the first socket again. The benefit from doing so is that now on each socket we have our own dedicated L3 cache. And so in the case of 2 replicas, both replicas can use the L3 cache completely on their own, and they don't need to share it with anyone else. And what we see then is, if we do it, we see the overheads for the single benchmarks drop dramatically. So for the 429 benchmark, we see that DMR is now as fast as single execution. We still have some overhead for triple modular redundancy. For the libquantum number 462, we see a drop to nearly no overhead, even in triple modular redundant mode. And the same goes for the last benchmark, where the adjusted version, where we put replicas on different sockets, also becomes fairly fast in double modular redundant mode and still has some overhead in triple modular redundant mode. And note that the overheads in triple modular redundant mode come from the fact that the L3 cache is when running 3 replicas on 2 sockets, the L3 cache is again shared between 2 replicas, exactly replicas 1 and 3, because they're still running on the same socket afterwards. And the outcome of this experiment is now that one thing, the good thing is we have lots of cores and we can use them for replication. However, multi-core systems are not homogeneous, and there are things that you need to be aware of, such as the cache layout of your underlying hardware architecture. And if you are aware of that, then you can distribute your replicas in a way that the overhead incurred by your fault tolerance mechanism becomes lower. However, if you are not aware of that, you may run into situations where you see significant overheads just because of caching effects. Okay, so here's an overview of how large Roman itself is. So in general, to implement all the features described before, Roman takes about 2,500 lines of code. There's some additional stuff going on. So we have some fault injector, which allows us to experiment and figure out whether our replication actually finds errors. We have a GDB stub in there, which eases debugging for replicated applications. And these are out of this a number of 2,500 lines of code. But if you see this, then if you compare it to the 7,000 lines of code we need for trap and emulate shared memory handling, then you see why we don't want to actually have trap and emulate in here, because this would dramatically increase the amount of code that Roman contains. Okay, so now the good news is that using Roman for replicating applications, we cover the whole user lane, and all user level applications, including device drivers and file system stacks, are now protected against hardware errors. However, I said before that we still have this reliable computing base down here, like the microkernel, the replication service, and the L4 runtime environment. And these services are not yet protected against hardware errors. So if a hardware error occurs while running inside these components, the system will still fail and we might not notice that. So what can we now do about minimizing this reliable computing base? We now want to minimize the reliable computing base, because if we keep it as small as possible, then for the one thing, we are less vulnerable, because the probability of being hit by an error while executing in the reliable computing base becomes smaller. And the other thing is, protecting the reliable computing base requires additional effort. And if we minimize the reliable computing base, then we also minimize the additional effort that we need to put into our system in order to protect it against hardware errors. So what do we do in order to minimize the RCB? One idea would be, well, let's say we have lines of code, and which is a metric for the complexity of the software we are working with. And in the trusted computing base in the security world, minimizing the TCB means minimizing the number of lines of code. And this makes sense for security, because for security, what you need to do in order to trust your code is you need to inspect the code and figure out whether it does what it is supposed to do and whether there are any security issues with it. And if this code is smaller and less complex, then of course it becomes easier to trust your trusted computing base. However, in the terms of the reliable computing base, this actually does not make as much sense, because we now want to minimize not the amount of code we want to trust, but the amount of code that is executed. And having fewer lines of code does not necessarily mean that you're executing inside the reliable computing base for less time. And time is actually the problem here, because the probability of being hit by, for instance, cosmic radiation is directly related to the runtime of your system. So the next idea would be, how come we minimize the time spent executing code in the reliable computing base, which seems like the reasonable thing to do, because I just told you cosmic radiation is distributed equally over time. So if I take less time to execute, I'm less vulnerable against cosmic radiation. However, the problem now is that there are some ways of improving speed of execution by using dedicated hardware units. For instance, you can improve memory copy operations on an x86 CPU by using SSE memory instructions, instead of writing the memory copy on your own using a loop that iterates over memory. The problem here is, while you speed up execution, you're now using more parts of your chip. And in addition to being equally distributed over time, cosmic radiation is also equally distributed over the area of your chip. So if you're using more area of your chip in a shorter amount of time, you may still be or still have the same vulnerability against hardware errors than if you're using a smaller part of the chip for a longer amount of time. Just because using more units will also increase your probability of being hit by an error. So what we in the end probably want is something that incorporates both. We want to incorporate the runtime that we spend executing inside the RCB, and we also want to include some notion of vulnerability, because even if you have a look at different instructions, they are not completely vulnerable in the same way. So you can have memcopy instructions which copy memory words from A to B, so they are vulnerable against errors in at least 4 bytes or 8 bytes, whatever they copy. Whereas you may have bitwise or bytewise arithmetic operations which are only very vulnerable against a certain an error in a certain byte in memory. So this instruction would be less vulnerable than the memcopy instruction. You might have other things that use certain arithmetic codes and are vulnerable against faults inside the ALU, while other instructions are not. And if you really want to analyze your system and minimize the RCB, you have to spend time looking at everything. And we're still working on that, so I have no results for you at this point. However, we spent some time thinking about how can we harden the reliable computing base once we minimized it. And what we need for that is we need some mechanism that allows us to protect anything that is part of the reliable computing base, so the kernel and the replication service in the easiest case. This mechanism might be implemented in both hardware and software. And the cool thing is, we have now, at this point, we have full control over the software, because this is the replication service and the kernel, and we are in control of it. At this point, we do not need to support binary applications, because our kernel does not come as a binary shipped. The replication service is no binary, and there is no notion of device drivers or any additional module that might be loaded. And so what we could do instead of using expensive radiation hardware is we could use either software mechanisms such as compiler-based fault tolerance, or we could use some kind of heterogeneous hardware. And if you have a look at modern architectures, then there are a couple of computer architectures that are heterogeneous in themselves. And one of them is the IBM Cell architecture, where they have different kinds of processors on the same chip. And one of the processors is a general purpose CPU, whereas the other processors are meant to improve computation work, but this is the only thing they do. They're not able to handle interrupts. They're not able to do memory access. They just do computations. Another example is ARM's Big Little architecture, where ARM ships you multi-core CPUs containing 2 kinds of processors. And one of the processors is a multi-pipeline architecture that is optimized for performance, but it's drawing a lot of energy when being used, whereas the other CPUs on the chip are low power CPUs with a smaller pipeline with no speculation turned on and so on. And the idea here is that you can save energy by using the little cores as long as the performance you get from the little core is enough to keep your system running, and only at the point where you want to execute something more computationally expensive, you switch over to the big core that draws more energy and thereby gives you better performance. And our idea at this point now is, hey, why can we not have a architecture that does a similar thing for reliability? And in our vision, we have a multi-core system consisting of reliable and non-reliable cores, and we call this resilient cores and non-resilient cores. And if we have such an architecture, what we could do is we could map our replication system by running the replicas that are protected by the replicator on non-resilient cores, whereas all components that are part of the reliable computing base are running on a resilient core. And of course, the idea then would be that a resilient core is protected using hardware mechanisms and therefore consumes more energy and takes up more space on the chip. And by actually not only having resilient cores, but having also non-res cores around, we could get better performance per chip area and per energy spent. We did some measurements with the Roman system on top of such an architecture where we basically simulated saying we have a multi-core system and we now say that CPU 0 is the CPU that is resilient and all other CPUs are non-resilient. And we played around with notification mechanisms because what you now need is you need some way of sending messages between the resilient and the non-resilient world. And the previous mechanisms I described where Roman intercepts all the system calls performed by the replicas did not consider the fact that we're now kind of switching between cores. We were simply assuming Roman has some way. And now we investigated various different ways. So one way is to send cross-core interprocessor messages, which are the yellow bars for these benchmarks. And here we see cross-core messages are actually fairly expensive because they lead to a very high overhead when intercepting exceptions. Another idea we considered was to use migration, where a thread that was running on a resilient on a non-resilient core would raise some system call, and this system call would not be translated into a cross-processor API, but the thread would simply be taken and migrated to a resilient CPU, so that the threads would move back and forth between the resilient and the non-resilient world. And if we do this, we're getting faster than sending synchronous messages around, which is good, but we're still fairly slow. And we actually found that the blue bars are the fastest solution to implement cross-core messaging. And in this case, we would place two threads, one on the resilient side and one on the non-resilient side. And the non-resilient core would just execute code. And whenever it raises a page fault, it would not send an API message, but it would simply write a word into shared memory. And on the other side, the resilient thread would poll this location by simply reading it all the time until it changes. And once it changes, it would know something needs to be done and it could then do the handling. So the lesson to take away from here is shared memory synchronization, which would actually be the fastest way of sending notifications on such a multi-core heterogeneous system. However, of course, this would still require memory to be protected against hardware errors. So one outcome of this experiment is we need some way of sharing or sending messages around very fast. And the good news here is that Intel already provides us with experimental hardware architectures that include specific cross-CPU messaging mechanisms, such as in the Intel single-chip cloud computer and its successors, such as Knight's Corner and Knight's Ferry and how they are called. And the second outcome of this experiment is that the boundary between the reliable and the non-reliable world is still vulnerable because in addition to raising faults while executing on the non-resilient cores, we of course might also encounter errors when sending a message between a non-resilient and a resilient core. And we need to make sure that these messages do not interfere with the replication service, which might be harder, but it's still something we're still working on. And as a last experiment, we also had a look at whether we can use compiler-assisted protection, because as I said before, we have the full source code of the reliable computing base, and we could therefore recompile the kernel and the replication service using existing fault-tolerant compilers. However, unfortunately, those compilers have already only been used for user-level code, and we're not aware of any compiler that is available that we can use to directly take Fiasco and our Roman service and simply compile it to see what happens if we protect the RCB using compiler methods. So what we had to do is we had to come up with some kind of a model to do that. And what we do is we have a detailed measurement of how Roman affects execution of an application when using replication. We can split the overhead into different parts, as we will see. And what we can then do is we can take the known overheads for compiler techniques, which range from about 10% for Swift up to about 400% for AN encoded processing, and can factor them into this model that we use for into the measurements that we did. And here's the model that we're using. So we start our experiment with the native execution time of an application. And this native execution time consists of two parts. One is the time the application spends executing application code. The second part is the time the application spends executing kernel code. If we now replicate this application, we still have this native execution time because this is what all the replicas need to do anyway. And in addition to that, we have more code or more time spent. Some of this time goes into executing code in the Roman master process. Some code goes into executing additional kernel invocations, which might be done by the Roman master. And we already saw that we also have hardware effects such as cache-related effects that go into the replication overhead. So these are the parts that somehow make up the time that we need for replicated execution. So we can break this down. So the overall execution time is native execution time plus replicated execution time, and we can split this into the components I showed you up here. Okay, what can we now do? The application code is protected by replication. So we do not need to recompile the application code using encoded processing or some other compiler technique. So in the protected version, the application code will still remain the same, or the time spent executing application code. In addition to that, we have kernel code and we have master code and we have some other effects. And these are the effects that will be affected by compiler level methods. So we need to take the time spent in the last four parts of replicated execution and multiply them with some constant factor, which comes from the compiler level technique which we use. This is the overhead that comes from compiler level protection. Then we make some assumptions. We say that we simply assume that the time spent in hardware is 0, so that we can simply say, well, we are aware of the fact that caching might be a problem, but for now we just ignore it and factor the overhead into the other three parts, so that we can say this is the worst case estimate for that. In reality, using compiler techniques to protect the kernel and the master will not have that high effect on caching than we now compute. But we still factor this in because it's very hard to factor the hardware cost or the hardware timing out of this whole equation. So this is why we rather would like to set it to 0. The other thing is we also set the kernel execution times, the yellow parts up here, to 0, because we did some measurements where it turned out that time spent in the kernel is actually like 0.01% of the overall execution time during native execution and during replicated execution. And so in this case, it's easier for us to assume that the kernel execution times are also 0. And this in the end leaves us with a formula for the protection time where protected execution time is the application execution time plus the master execution time multiplied by a constant factor stemming from the protection mechanism. And we then did this. We again took the spec-int benchmarks, which we already measured before. And we then took the triple modular redundant version with Roman and added the protection using Swift and using encoded processing. And what we see here is, for instance, for the Perl benchmark up here, the red bar is triple modular redundancy in Roman, which has something like 2.5% overhead. Using Swift would not much increase this overhead. Using encoded processing gives a bit higher overhead, but it's still about 10%. We have some other executions where we have like 25% overhead for encoded processing, and we have this benchmark down here where encoded processing would actually lead to something like 60% overhead. What we see is that combining software-based fault tolerance methods like compiler-assisted fault tolerance for the RCB and replicated execution for user-level applications has actually a much lower overhead than the overhead that we would get from using encoded processing alone, for instance. Like the average overhead in encoded processing is about 390%, and here the worst case overhead we see is 60%, which is a much better performance gain. And this is also something we're currently investigating. So what we know now is it seems promising to combine these two methods. However, this is only the performance-wise comparison. And what we still need to do is we need to compare how many of the errors that encoded processing would detect if we compile the whole system with encoded processing is also detected when using replicated execution. And another thing is resource overhead, which is also not factored into this equation. So there's still a lot of work to do, and we're still considering doing that. So as a summary, in my 2 lectures today, I presented you operating system level techniques that allow you to tolerate software and hardware faults. The important parts are that address spaces allow you to isolate applications from each other and therefore make sure that a fault in one application does not affect other applications, which is important for both hardware and software faults. Building your system as a microkernel allows you to have very small components which can be micro-rebooted, thereby improving the error recovery times. And I also talked about the various ways of how we can handle session state, what we can do against hardware errors, and I hopefully convinced you that there is still some work needed to do to protect the reliable computing base and to come up with solutions that allow us to do so efficiently. And this concludes my talk, and I'm happy for any question to answer any questions you might have. And apart from that, I wish you well and have a good day. Thank you.